Hello, everyone, and thanks for coming this morning. Apologies for my conditions not being the nicest ride this morning. So today I'm going to talk about the workflow that I've been developing with AstraZeneca in collaboration with the University of Cambridge and Lapkin Group, where I'm trying to automate DFT calculation to integrate them within reaction model and reaction feasibility routines. So just to introduce a bit what is reaction development and what is the goal that we are trying to achieve when we do this kind of processes. The main goal is always to develop reaction that are better, that we can improve the yield or the selectivity, for example. And the overall goal is that we want to bring drugs and synthesize drugs more quickly and in a cheaper and more sustainable way possibly. So the idea behind all of this is to build models, like computational models of reactions that are with which we would be able to predict what could be the best condition, what could be the best building blocks, and so on. So I created this like very approximative scheme of what could be considered some of the areas that engage in reaction development. And as you can see, there's like very different topics. So we have experimentation and all the techniques that have been developed, such as high throughput experimentation, robotics, automated labs. That these help like improve the scale of the reaction that we can do, improve the consistency, the reproducibility of the reactions. Then we have chemoinformatics with techniques such as statistical techniques such as QSAR or machine learning, where we can build models from all the data that we gather. And then, maybe this is a bit of a personal bias, I also added computational chemistry, because with computational chemistry we can build mechanistic models from the theoretical basis and understand really what's going on in the reaction and use this knowledge to predict the outcome. So in this talk, I'm going to focus on mainly computational chemistry and the interface with chemoinformatics. And if we look a bit closer, what are the differences between a data-driven and an ab-initio approach? We see that machine learning, as probably most of you know, tries to extract knowledge from the data that we have, tries to find patterns in the data, and sort of build models that predict new data. So to build like very good models, you usually need good quality data and quite a lot of data. And generally speaking, you're limited to what your training data samples in the chemical space. It's difficult to extrapolate. On the other hand, we have ab-initio approach, such as quantum mechanics or DFT, where the knowledge is derived from a theoretical basis, so from some physical foundation, and we don't really need to know anything about, like any previous knowledge about the system apart from, I guess, like the atomic composition. But unfortunately, it's very computationally expensive, especially if you want to treat this in a routine way and apply it to quite a few reactions, for example. So in my project, we are trying to combine the two. But really what we mean with combine the two is, it can mean different things combining quantum mechanics and machine learning, and there's a lot of that has been done in the field. For what concerns this talk, what we're really trying to do with quantum mechanics is to bring to use physical observable computed from quantum mechanics as features in your machine learning model. So if we look at how usually what is the workflow for a quantum mechanics routine, you run your calculation, you extract some physical observables from your calculation, and you use that to explain or predict an experiment. Whereas when you have machine learning approach, you gather from some historical data and you add some molecular representations, some molecular descriptors, you build your model, and with that model you predict the experiment. So what we're trying to do here is to just plug in some physical observable from QM and use them as descriptors. So it's nothing really new, and a lot of physical observables have been used to, let's say, improve machine learning models, such as electrostatics, electronics, and so on. But what we really think is the key here is to add also thermodynamic and especially kinetic parameters in the model, like QM computed kinetics parameter in the model, because it has been shown that can really improve the quality of the prediction. The limitation and why people haven't done extensively is that obtaining this kinetic information from QM is usually very expensive. So very briefly speaking, what you really need to do is to compute to get the information about, for example, the rate constant of the reaction. You need to calculate the difference in free energy between the transition state and your ground state. So usually this, I mean, it's a fairly complicated calculation, but once you have this delta G, it's directly proportional to the rate constant, and it's a very informative parameter. Unfortunately, the real case scenario, when you have complex reaction, you have multi-step process, and calculating the free energy barrier for each of these process, for each of these steps, can be very computationally expensive. There is a lot of expertise that comes into that, and let alone there's a lot of like practical work that you need to do to set up this calculation, to run this calculation, and to analyze this calculation. And I know what everyone says, that they are expensive because we don't have enough computational power, but I had the luck or the privilege to work with quite a lot of intensive computers, and you quickly realize that you are the rate limiting step. If you cannot analyze, I don't know, 500 reaction in one day, the computer is much faster than you in that case. So what we really want to do in our project is to build an automated workflow that is able to compute these free energy barriers automatically, or at least semi-automatically, so that you can use these calculation in a routine way and sort of use them as fundamentally a molecular descriptor for your data-driven model. So what we believe are the requirements for such an efficient integration and for such workflow I divided them in two different types of requirement: chemistry or computational chemistry requirement, and the workflow, so the requirement of the software. So the computational chemistry requirement are definitely like, it has to follow rigorous computational chemistry practice. So we want to compute conformers, we want to generate conformers, we want to optimize and calculate frequency, have frequency calculation, integrate solvation, and so on. It has to implement a versatile choice of theoretical method, which means as a user, I should be able to select to be able to select different arrays of theoretical method, because in certain occasions I might want to have something a bit more detailed, a bit more computationally intensive. In other tasks I want to be a bit more crude, let's say. And so having this versatility allows you to actually deliver better result. And finally, the most important thing is that we need to be able to produce automatically key geometries. When I say key geometries, I mean the transition state and reaction intermediate that I was showing before. From the workflow point of view, since all of these types of tasks are handled by different software, the different computational chemistry package, the workflow should be able to handle different input-output formats and options from the different computational chemistry package, and should be able to, I have to just press a button and not care about, setting up the different input and output for every software package. As well, it should be able to interface with scheduling systems such as LERM, and ideally, it should involve minimal user intervention. So the solution that we come up with in the molecular AI group in AstraZeneca is called Maze, and it's a software. It's an open source program that we developed, so it's up there on GitHub. There is a preprint out probably soon is going to be published in a peer-reviewed journal. So basically speaking, Maze is just a workflow manager. So it's a software that basically can connect different programs and organize the execution of this program in a, let's say, predefined way. And it's based on directed acyclic graph scheme and on the principle of flow-based programming. So a workflow really looks like a series of nodes, and each node is an instance of an application. So this is literally like, it's written in Python, I forgot to mention. And so it's literally just a Python script that executes a bunch of commands. So some commands could be the interface with a computational chemistry software, or some commands can be just merge two smiles or select this type of reaction and so on. So the nice thing about flow-based programming is that each node is a separate process. So it means that intrinsically you can parallelize this kind of processes, especially depending on the setup of the workflow that you decide. So for example, this is an example. You can create all sort of graphs, all sort of connection and logics. And so this is really like the flexibility and the versatility of this workflow, of this software is really interesting. And so it was originally developed for active learning, and then I just created the setup for Gaussian and other computational chemistry software. So if we quickly look at how I built my workflow, it is composed of mainly 3 subunits. So we have the first big node, which is reaction control, that reads data from an experimental, there is experimental data from basically a CSV file. And in this data, there's all the information about the reaction that comes from the lab. And here is where all the input files for the calculation are generated and then are sent to the 2 separate sub-workflow. The first one, where we generate the conformers for each of the reaction species. And the second one is the geometry optimization, where we optimize the geometry and calculate the frequencies. So if you look very quickly at how all of these 3 subunits work, we have the first one, which is the automated generation of the geometries. So as I mentioned before, the data comes from the experimental lab, like from the lab, but it's literally just like a CSV file, a series of smile string for every component of the reaction, and the node just reads this smile string and creates the 3D structures. And then for the relevant geometries, we have a predefined reaction class, which contains the set of transformation that you want to include in your reaction. So we've done it manually in advance. And the user just has to select which reaction class it wants. And it generates the relevant geometries for every component. So for example, this is what will look like and what we'll send to the calculation node. So you'll have instances for each of these molecules, and each of these will be treated as a separate calculation. So the interesting part is how we create these intermediate and transition state geometries, because of course these are the complicated ones. So the approach that we followed is to use some predefined, pre-optimized scaffolds, where we basically strip we optimize with DFT some structures, and then we just strip the intermediates or the transition state from the ligand, and we just use placeholder atoms. And these are used as blueprint to basically build transition state and intermediates for reactions for different reaction of the same type. So for example, this is what will look like. There is a series of geometrical transformation that like the function that are all implemented in the program, that basically will adjust the geometry of the ligands to sort of like create a decent initial structure. So this then goes to the conformer generation sub-workflow. So, as I said before, the geometry that comes out of the initial step are still very crude because it's literally like there's no knowledge about chemistry. So in this case, we just run a quick molecular mechanics pre-optimization to remove any spherical strain, and then we do conformer generation with CREST, which is a metadynamics method based on some semi-empirical calculation. So for each of the components that I showed before, the conformers are generated and are passed through the next step, which is the optimization and the frequency calculation. So we run geometry optimization. So the default method is to use XTB, which is again a semi-empirical method to optimize the geometry. So this is a bit less, it's not as accurate as DFT, but it's much, much quicker. And this will be our default setup where we run the optimization with XTB and then we do a single point calculation with Gaussian at DFT level. So again, this is something that is not, you can modify all of these, we can modify all of these settings based on what are our needs in that specific case. And finally, the results are sent back to the reaction control node where we have a bunch of functions that automatically identify errors in the calculation. And based on the error, on the type of error, we have some predefined action on what to do. For example, if you have a timeout, you might want to resubmit it. If you have a convergent issues, you might want to scrap that calculation altogether. And finally, once all these calculations have been completed successfully, the key properties that we're interested in, such as the delta G's, are calculated and then basically appended as a column to the original CSV file. Just to conclude very quickly, the computational resources and performances are, I guess, like a very critical thing. Of course, like as I said at the beginning, we have at disposal like quite large number of computational resources with the AstraZeneca cluster. But what is our goal is to, let's say, being able to compute a small library of reaction within one night. That would be the ideal goal. And so, for example, to run 50 of these individual workflow, which each one of them is a reaction, within 8 to 12 hours. And usually, in my experience, like a reaction of 14 components can usually run within 6 hours. It, of course, depends on how busy is the cluster in that day, how, like really a lot of things. And, there's a lot of problems also in industry. It's not everything nice and infinite resources. The idea, though, is that being able to just select the parameters and the type of settings that you want for each of these software allows you to, I guess, like find the optimal balance between the accuracy and the cost for your specific setting. So right now we are studying 2 reactions with this model, with this workflow, and one is the metal photoredox carbon-carbon cross-coupling, and the second one are the carboxylative Gies and Minishi reaction. So, final remark on the limitations and the future direction of this workflow. I guess the main limitation is that knowledge of the mechanistic picture is required, which means that for all these templates that I showed you before, these transitions, these intermediate have to be known in advance. Like the workflow is not able to generate them automatically. So this is a method that for now is only suitable for reaction that we have at least a knowledge of the of the mechanism. It is still a very computationally expensive approach, which means that it might not be the best pick if you have a lot of data available. So if you have a lot of data available, there's no point in running all of this. And the idea is that, as I said, I guess like as I said before, that this solution is really more aimed at situation where we do know the reaction, we don't have much experimental data to work on, and so we can compensate with the QM calculation. So the future directions that we are going to take are definitely trying to integrate automated reaction pathway identification for two main reasons. First of all, the issue of side reaction is really what hampers this method, because if you don't have good knowledge of side reaction, you might have a very good mechanistic picture, but if the main reaction pathway is not the only one, you won't see your prediction performing really well. So that is something that, it's inherently dependent on the reactant and the building blocks and so on and so forth. So it would be nice to have this kind of integration. Secondly, what would be really important as well is to be able to generate automatically such transition state intermediates, and there's a lot of programs out there that are trying to achieve this, and we have someone in the group as well that is working towards this direction. And finally, I guess this ties back to what I was saying before, expand the scope of reaction available. So far, the reaction that I've been developing are the reaction that the people that I work with are interested in. So of course, it's always nice to expand, but I guess it's also like a question of, you can't really compute, like have a predefined class for every single reaction. So there's a limit there that we need to find. And finally, one of the options that are currently being developed in Sweden are the development of machine learning potential to sort of substitute some of the DFT or semi-empirical method and basically reduce the overall computational cost of all this process. So I guess that's pretty much it from my side. I'll just have a few people that I want to say thank you to. I guess, first of all, XA and the Lapkin Group and the IDMT for, I guess, hosting me, and all the people in AstraZeneca that have collaborated with me, both from the UK and Sweden. And yeah, so if you have any question, I'll be very glad to answer. And thanks.